Hello everyone, my name is Yoshinari Takegawa. I am an Associate Professor of Future University Hakodate. I'd like to present our research Digital Full Face Mask Display with Expression Recognition using Embedded Photoreflective Sensor Arrays. This work was co-authored by other members of Future University Hakodate, as well as members of Keio University and UCL. To illustrate our work, I'd like to start by showing you the demonstration movie of the proposed digital mask. E2 Mask Z is a digital mask that can change the appearance of your face in any way you like. Unlike conventional avatar-based face-to-face communication in a virtual environment, E2 Mask Z can augment the wearer's facial expression with a favorite avatar in any real environment. Our integrated system embeds optical sensor arrays on the inside of the digital mask display to sample facial movement and utilizes a machine learning technique to recognize the wearer's facial expressions. The face is the most expressive part of our body and is one of the important parts that decides the impression a person makes on others. To create a desired persona that exceeds the physical limits of human faces, people have used digital avatars as more effective and flexible media to control the impression made on others in a VR environment. For example, in a remote video communication system, a speaker can digitally augment their real face by altering the appearance of a 3D avatar on a computer screen to look the way they want it to. On the other hand, researchers have also investigated several digital face augmentation technologies to customize facial expression in a real environment. To the best of our knowledge, these prior digital face augmentation technologies have lacked facial expression recognition capability, so users cannot control their augmented faces intuitively. To enable avatar-based face-to-face communication in a VR environment, researchers have investigated computer vision methods to estimate the facial expression of head-mounted display users. For example, headset removal and Face VR model the facial expression covered by a head-mounted display using machine learning techniques and reproduce the dynamic facial expression to an avatar's 3D face model. Although these methods provide robust facial expression recognition capability, the augmented avatar face is visible only in a virtual environment and thus not applicable to face-to-face communication in a real environment. To digitally augment the face in a real environment, we have previously explored a camera-based digital mask display, E2 Mask. As the critical design problem, 9 inches of camera-to-face distance is required to recognize a full facial expression, which makes the digital mask display too bulky to wear and walk around in a real space. To address the wearability issues of face augmentation technology, we present E2 Mask Z, a digital full-face mask display with facial expression recognition capability. E2 Mask Z integrates a thin, flexible face mask display with photoreflective sensor arrays to enable facial expression recognition at a millimeter-short range. The integrated system identifies the wearer's facial expression based on the photoreflective sensor data and produces an avatar presenting the same facial expression. The 40 photoreflective sensors are laid out on the inside of the face mask display. We deploy an OLED-based flexible face mask display to keep the distance between the photoreflective sensor arrays consistently at a minimum distance from the face and smoothly overlay the convex human face. The workflow process of E2 Mask Z follows 3 steps. The face capture mask first samples the wearer's facial expression at 40 feature points around the eyebrows, cheeks, eyes, and mouth. Given sampled sensor array input, the system identifies the wearer's current facial expression utilizing the trained support vector machine model. Finally, the face mask display renders the identified facial expression to the avatar face on a curved display screen. E2 Mask Z can identify 10 types of facial expression. We selected number 1 to number 5 based on the constant expressions defined by Ekman. Number 6 to number 10 are the facial expressions formed when pronouncing Japanese vowel sounds. We chose support vector machine (SVM) method to identify facial expression as it has the advantage of low computational cost and its feasibility for facial expression recognition using photoreflective sensors had been reported in prior work. We use RBF kernel and C=10, gamma=1.0 as hyperparameters. The avatar's facial expression parameters, vector P, such as the degree to which the left and right eyes are open and the width of the mouth, as shown in the figure on the right, can be composed by the formula shown here. This method refers to the work of Suzuki et al. We recruited 7 university students, 4 female, 3 male, for an experiment to confirm the facial expression identification accuracy. In the process of the experiment, each subject first put on the prototype mask, then was instructed to imitate facial expressions number 1 to number 10. For each facial expression, 10 data samples were collected. Since we repeated this experiment 6 times for 10 different facial expressions, we acquired 600 samples in total per subject. It took about 3 minutes to collect 600 samples of data. 6-fold cross-validation was applied to the sample data. As a result, the accuracy was 79%. We think this constitutes high accuracy, but we need to improve the accuracy of anger and surprise especially. Among the correct data for surprise, 63% were estimated to be surprise, while 12% were estimated to be ah. In contrast, among the estimation data for surprise, 15% were correct data for ah. From these results, it can be said that the surprise facial expression is being misidentified as the ah facial expression. The facial expression with the second lowest accuracy was anger. The high rate of misidentification in anger and sadness could be due to the fact adult subjects don't express anger or sadness daily, leading to the difficulty of producing clearly discernible expressions. To evaluate the feasibility of E2 Mask Z, we conducted user experiments to compare the sense of self-agency and self-ownership toward the controlled avatar between E2 Mask Z and a camera-based digital face mask display, E2 Mask. We recruited 4 female and 3 male university students. The task of the experiment was to reproduce 5 emotional states of facial expression. The subjects were instructed to practice facial expression control of the augmented avatar face for up to 20 minutes for both digital face mask displays. After the practice, we asked each subject to wear one of the digital face mask displays and guided them to a seat facing a wide mirror so that they could look at their entire body with the augmented avatar face reflected in the mirror. To make a counterbalance, we asked 4 of the 8 subjects to start the experiment with the E2 Mask Z and the other subject group to start with the E2 Mask. All the subjects were asked to memorize the top 5 emotional expressions, then reproduce the facial expressions in a randomly instructed order without the reference images during the experiment. After the end of the experiment, we asked subjects to answer 3 questions about the usability of the 2 digital face mask displays. Question 1. How well did the avatar recreate your intended facial expression? Question 2. How smoothly did the avatar's facial expression change? Question 3. How strongly did you feel a sense of self-ownership toward your augmented avatar face? Subjects answered on a scale from 1 to 5, giving reasons for their answers. Question 1 and Question 2 evaluate the sense of self-agency, and Question 3 evaluates the sense of self-ownership. This table presents the mean value, the standard deviation, and the significant probability of both E2 Mask Z and E2 Mask for each item in the questionnaire. Regarding the average value, a smaller value indicates a more positive response to the question. Overall, the subjects showed positive responses regarding the sense of self-agency for reproducing the expected augmented facial expressions with both digital face mask displays, and there was little difference between E2 Mask Z and E2 Mask. The proposed method can currently only recognize 10 facial expressions at the same time. To address this limitation in our future work, with more high-density micro-photoreflective sensor arrays, we plan to construct a 3D physical facial model and track micro-expressions to enable smoother facial expression transformation on the augmented avatar face. The potential mismatch of the sizes of the digital face mask display and the face of the user is another practical problem to address. When the mask was much smaller than the user's face, some photoreflective sensors touched the face and failed to obtain the corresponding facial features correctly. As a simple solution, an extra nose pad or padding around the edge of the mask can be added to overcome a small range of mismatch between the facial feature points and sensor array positions. To overcome significant size differences, we must make new masks of different sizes to allow us to cover a user face size range that includes particularly small or large faces. As applications of E2 Mask Z, we can think of enhancement of facial expressions for patients with amyotrophic lateral sclerosis, ALS, a method to relieve fear of the dentist for child patients, and reduction of emotional labour for workers in customer service, controlling the face of an interviewer to ease an interviewee's nerves, and augmenting the faces of performers for immersive stage performance. That concludes my presentation. Thank you for your attention.